So, good morning, everyone. Let's start our morning session. The first speaker is Professor Philip Walther from the University of Vienna, and he's going to talk about quantum photonics for quantum causality and other quantum information tasks.
Okay. Thank you very much. It's a pleasure to be in Natal again. Many things have changed since my last visit, and it's impressive to see basically how basically this institute now became such a nice environment. As you can see from the title, I would like to present you or show you results of two different fields. One is related to causality, where yesterday Julia was already giving a nice overview about the recent results, and I would like to start from there a bit and give you a broader context picture of why we're interested in that and why we're going to use photons as the quantum technology that allows to investigate those things. The second part here is up to you. I have in mind to show you two additional results that we recently did in our group. One is enhanced communication, where we can use just one photon to do something that's classically impossible. Or if you're more interested, I can show you how you can boost the security of classical computers by using feasible technology. Okay? I'm not sure if you can do both, so is there some preference, or should I just go ahead and we see how it goes, and then you can decide as the customers here, okay? If you would like to have rather one or the other, okay? Is there any, please, feedback, okay? Otherwise, do not continue. Number two, rather? Okay. Good, then we can jump to that. Good. Well, Vienna just is a city here. Just to give you back up who we are. We are located at the Vienna Center for Quantum Science Technology, where we are basically three academic institutions. University of Vienna, that's where Časlav and myself are from. There's the Academy of Sciences, where also Časlav is linked to that, and there's the Technical University. And as you see, a link basically, there's a strong link between experimental groups, for example, as mine and Časlav, which is a nice basically framework that we have there. That's a picture of the group. So today I will show off stuff that I haven't done personally, but these experts, and one of them is here, Julia. If you have questions related to things I talk about that she did, please don't hesitate to bother her. Good. What do we like to do? We see ourselves as quantum photonics people who, on one hand, would like to build quantum computers and address all the challenges. That means we investigate technologies for photon-photon interactions, different sources. But we're also interested in foundations, which is at the root of the Vienna research. Therefore, we also investigate foundational questions. And something we'll not talk about today is also the interface of quantum physics and gravity, which is also happening with Časlav right now these days. Good. Brief backup, why photons and what's so nice about the systems. For those of you who are not familiar with optics, photons are a very nice stable quantum systems where you can encode information by various degrees of freedom. Most often it's used polarization degrees of freedom. Horizontal polarization denotes a 0, other one a 1, because it's so handy. You just need a phase plate and you can address the entire Bloch sphere easily with highest precision to prepare your state. Otherwise, you can also use path degrees of freedom, where one path defines a 0, other path defines a 1, and by just using a beam splitter, you can tune the probability where the photon is located, and therefore also prepare your state here as your degree of freedom. So very nice. You can also combine those. So in contrast to many other quantum systems, you can easily address different degrees of freedom, which allows you to hyper-encode quantum information in the photon, and that's something which also is very nice in terms of being resource efficient. You don't need to prepare as many photons as bits that you would like to use. So photonic quantum computer in a nutshell is built out of three boxes. There's the source part, then comes the circuit where you process your photons, as shown here with this kind of, nowadays it's fancy to have these integrated waveguides, and at the end, detection. If you ask me what's the challenge to be scalable and build up as big as we would like to have quantum computers, problem number one is loss. Okay, so we fight very much against photon loss. If this is solved, we have almost everything done. The other challenge is to have good photon sources. Nature, unfortunately, doesn't give us Fock states for free, so it's very hard to get a single photon, and it's even harder to get a single photon when you wanted to get it. But we work on that, and I'm optimistic that photons have a very nice future ahead, in particular facing that they are the natural choice for being mobile. You can communicate, and you can also link it to computing, where you transmit photons or distance, compute here, and come back. That's a nice feature. That's a picture of a real quantum computer chip. So we have, for example, these kind of integrated circuits where 6 photons can be processed. You tune the phase shifters, and here you can, for example, implement different unitaries. That's not sufficient for the full universal quantum computer, but it allows you at least to do interesting parts by defining the unitaries in that. As I said, losses is a challenge, so what's the problem number one? Detection. So these days you can achieve almost 100% detection efficiency by using superconducting technology, where, as shown here, we have a single photon coming in here, superconducting nanowires. They're efficient and fast. The other thing is you would like to be ready again to see another photon once you detected one. And here you see nowadays that we really achieve very high efficiency, really close to 100%. So there's progress, but there's still a long way to be really universal in the sense of building big computers. And that's a real picture of the cluster that we use. Good. Last things to show, sometimes you would like to have entanglement right away. The standard way to do it, now used for more than 20 years almost, is down conversion, where probabilistically you take a blue photon, for example, and then you split it by nonlinear process into two red photons, which are different polarized. If you take them from the cross-section here, then you can obtain entangled states up to 99% fidelities, almost on a regular basis these days in the laboratory. That's a picture of how it goes in real life. So what you see here is the down conversion crystal, and the laser shoots through the crystal into your eye. When I start tilting the crystal, at some point you see how the phase matching works. The nonlinear process can be established, and what you see is then, oops, no, that's too fast. You can see then that here's the one single and idler, the two down-converted photons with different polarization, and the magic happens when you catch photons from the intersection points here and there, where you don't know whether they emitted, and if you do it properly, then you really get these highly entangled states that we use for computing or other information tasks. Good. I briefly want to give an overview why we're interested in this indefinite causal order business. As yesterday nicely presented by Julia, it's a very nice twist about quantum physics, and for me the keystone papers were actually those three. It started with Lewis and Hardy, who's shown that when you superimpose masses and you have this basically superimposed space-time, you naturally lead to indefinite causal structures when you do a computation. The next two papers, but that's a personal opinion. I think there are way more papers in between, but these were for me the keystone, the cornerstone papers. One by Jaslev, who showed also that you really have these quantum correlations in an indefinite causal structure. And there's the work also by Julie Carabello, who introduced the quantum switch as a nice framework to see how you can basically draw circuits that explain how these indefinite causal structures work. So this is obvious. That's basically what we mean by causal relations. Something comes before the other event, A before B, or other way around. Sometimes you have two coexistence like this. However, we talk about superposition. For me, as an experimentalist, you always have in mind states that you superimpose. For example, spin up, spin down, or polarization left and right. It was for me very interesting to see and to learn that you can also superimpose orders or causal relations as shown here. And since we are interested in computing, you immediately see the benefit for information tasks when you replace A and B by computational operations or unitaries as shown here, which in a basically big picture means when you have a computation and now you're allowed to superimpose the gate orders, which is different to standard architectures, you suddenly have coexistence of different softwares. So the challenge now here is, of course, can you find computations that are now better or perform more efficient than standard architectures? And the answer is yes. Okay. So as an experimentalist, you try to investigate those things. So where do you start? You first try to find an apparatus that can do that, and photons, yes, you will see, is a nice option for doing that. The other thing is, as I've seen, we would like to show applications. So we investigated, can we do computations that are now better or more efficient than a standard architecture? And then, which was actually, to be open speaking, not really on my radar in the beginning, was the challenge for ourselves: do we really have this kind of indefinite causal structures? Can we be sure that there's not anything else happening? Okay, and that basically enters automatically the business verification of your systems, of the situation that you prepared in the laboratory. And then you see there's different layers. So you can start with a quantum mechanical framework where you use witnesses and so on. We'll show this in a second. Or you can even basically put a higher level of test by say, well, we can even make this in some kind of theory-independent way, as shown yesterday with Julia. And the journey will not stop here, so I'm very optimistic we're going to continue. We'd like to investigate more, be more confident that this is the case. We have these indefinite causal structures with more complex operations. And of course, we're also interested in finding new interesting twists where those things do something good for you. Okay? We like to show there's a benefit, not only for fundamental reasons in doing so, and so on. There's plenty of literature. I picked some of you. Here you see on the left side results where people were interested in optimizing tasks. There's nice work by Julie Kirabello as well as by Chaflos Bruckner's group who showed communication can be enhanced. The different teams, different ideas how these indefinite causal orders boost your communication tasks. And there's also very nice result showing how you can find methods, witnesses that allow you really to tell you, yes, you indeed have this kind of indefinite causal case. Now, I sweep through. I had in mind to change the slides, but yesterday was rather long, so I have it to do it now. So just a few slides now, why photons? So the scheme works normally like this. You have a target state where the psi goes either one path, U1, U2 first, or the other way around. Okay, these are different causal structures. The other thing you need is a control stick. That's the control bit that tells the target state what to do. So 0 defines this path, and the 1 state defines the other path. And if you superimpose the control bit, you basically have this coexistence of both causal events or an indefinite causal structure. The nice thing is that this kind of task, as I showed before, allows you, for example, to have faster computation. And one thing we have shown is that you can basically, with one shot only, investigate are those operations commuting or not. That cannot be done by a classical quantum architecture or standard quantum architecture as efficient. So in a nutshell, you can achieve these speed ups with respect to quantum algorithms that are standardly built, but of course you also have a huge advantage compared to classical computations, as I said. So why photons? As I said, you have different degrees in freedom of hand in your hands, which means you can put the control and target bit into the same photon, which is very handy. Okay. So the easiest way to understand is, for example, by such a circuit. A polarizing beam split is a device that splits the different polarization. If the photon is horizontally polarized, it goes this way, always transmitted. If it's vertically polarized, it's always reflected. Now you see how the circuit works. An H photon, horizontally polarized, goes straight. First this operation, goes straight again, comes out here, comes here straight, then this operation and goes out. So first U2, first U1 and U2. If it's orthogonally polarized, reflection, first this operation, reflection, here reflection, and you basically have the other order. And if you superimpose, you see you have those basically in coexistence, which a computer's circuit would be represented as this quantum switch. These are my words, just as the equation. But here you see very nice that you can, by superimposing the states, really achieve the coexistence of A first and B and vice versa. And you can then afterwards project on the complementary state to investigate, is there plus or minus sign, or do they commute or anti-commute by just one shot only. In the experiment, we changed a little bit the configuration, but the spirit was the same. We used not a path for technical reasons. The path is the control bit. That means if the path is straight, it's a 1 state. If the path is reflected here, it's a 0 state. And then the target state was affected by a different degree of freedom. So path is gone, so I had to use polarization as our method to implement here the unitaries, one first this and then the other. And then basically by one shot only we could investigate here this kind of do they commute or anti-commute. That's the setup. So we had the down conversion as showing before. One photon is just a trigger, the other photon comes in here and then enters either this path as the defining one order, first this and then the other order, or is reflected and then basically give the other order as first this reflection, this order going through the interferometer and so on. Good. The first experiment we did was to investigate do they commute or anti-commute with one shot only. So the 101 questions to you guys. We had two operations in there. And if you had, for example, poly operation X and Z, first X and then Z, or vice versa, do they commute or anti-commute? 101 in physics. Of course, they do not commute. So we had basically one output. So blue means we get as result not commuting. If you had, for example, twice the same operation, here X, they commute. You see it's a green tower here. We got a result, they commute by one shot only. Being more interesting, having not only the basic quantum Pauli operators, we use different unitaries which have been chosen to be commuting, anti-commuting, and we had a bunch of runs, and a very high success rate. You could really got the result by one measurement only, are they commuting or not in this case. Good, that was the first beginning. Then people very smartly raised questions, more from the computer science. Very nice what you have shown, impressive that computers can even superimpose the software, but are you sure you're really using indefinite causal structures? Isn't it like that you haven't found maybe some better quantum algorithm, quantum protocol? So how do you basically address such a challenge, okay? So you have to look at your device and say, yes, we want to know what's happening inside and convince people, yes, you have these indefinite causal structures. And that's in the spirit of verification. Briefly, that was shown yesterday also by Julia. We implemented a witness designed and developed by these kind of people, Jaslav and Araujo and Banciat and so on, Costa. And they basically developed a process matrix where you can apply a witness that tells you at the end, are you having this indefinite causal structure or not? We had to do a bunch of measurements. I just will briefly mention that, where you choose different input states, different operations A and B, and the output state. The thing I'd like to emphasize here, even though it looks like the same we did before, it was a major step in terms of technology, because we replaced one of the operations at Alice's side, not by a polarization operation, polarization flip. We really implemented a measurement device. In principle, those operations can be anything you have in mind, and we really faced the challenge to implement a measurement operation and a preparation stage. So what you see here, even though it's a messy picture, that at one side here we have this PBS inside, which is a measurement device, and basically we got either 0 or 1 as output. You see there are two beams because we had interferometrically align everything. That doesn't matter if A comes first or B comes first, everything must basically within the circuit indistinguishable, which was a challenge. We also had these two output ports, and there was the experiment. We have to get a lot of credit to Julia to really manage the tasks to build this setup when our measurement was in there, which allows to have a stronger confidence, a stronger violation of the witness that tells you, yes, you have the indefinite causal structure. Good. What do the experimentalists do to see the dependency of your device with the result you obtain? You tune something, and the easiest thing to tune is you misalign your machine. So here we see basically the quality of our interference. That's the best interference, 1, that's the worst interference, there's no interference happening. If you have 1, see we are above this threshold, and we really have this witness telling us yes by a number. We do have this indefinite causal structure. If you misalign the paths, that means we have slightly distinguishability coming up. Then we see how this number gets smaller until it comes to the case where you would enter a classical regime where there's no coexistence of both orders. This I will rush through. As I said, one step further was to make a test where there's no quantum mechanical rules assumed anymore. Basically, it was the plan to have this theory-independent experiment, and for that we have to grab the toolbox for Bell inequalities, as shown yesterday, where you have to phrase everything in such a way that, in a nutshell, if you obtain at the very end a Bell violation, it can only have happened because you had on Alice and Bob's side these indefinite causal structures. So in a nutshell, the setup was built in such a way that you can exclude all other problems, all other tricks, where nature would give you the result of the Bell violation, such at the very end, the only reason why the Bell violation happened, because you had uniquely these indefinite causal structures coexistent on both sides. And that's basically how you phrase it here. So you define a separable state, a causally separable state. You can see the two parties now, as shown by Julia yesterday. We had these assumptions, we'll not go through. Assumptions are set up that you really prove, again, indefinite causal structures must have been the mechanism to give you a Bell violation. So this was basically the experiments of yesterday. You had now 2 times the indefinite causal boxes where you superimpose on each side the orders, and you choose basically similar to shown yesterday what's happening, either first these kind of orders or other orders, this laboratory first, now this laboratory first on each side. And when you start with a control bit, which is an entangled state, then you can really achieve that the target state is entangled. So you start here in a separable state fashion, you choose the right control state, and then at the end you rush through, you get this entangled state, which allows you to tell you, yes, you had these indefinite causal structures. Good. this is also something shown yesterday, so these are the experimental parameters. I will rush through, it's not important, but it was the tune. Also here, the strategy is the same to be sure that you know that what's happening, and you misalign something to see the dependency. So what did we misalign? And one thing we misaligned the quantum switches on the side, and you see how the Bell violation goes down, of course, because that's the mechanism needed to achieve that. Or if the control bit, which basically establishes to the target bits the entanglement, if this one is decreased, if the amount of entanglement, then you see from ideal case to a separable case, you see also how the violation goes down as a control mechanism, what's happening in there. Good, that's in a nutshell our approach for indefinite causal structures. As I said, photons for me are the natural choice to investigate those things because of being mobile and having these different degrees of freedom in one system. I rush through because I'm really excited to tell you the other stuff, and I have 40 minutes. I take the risk and try to give you an overview about both things that happen, because this might be more in the spirit of this conference here. So I change gears, no indefinite causal structures anymore, but still superposition of something. So based on a recent result, we were interested in the basic concept. I think for me the beauty in quantum information can be found in a simple case. Okay, take one single photon or entangled pair, and you have beautiful applications. You know all of them. Basically, they fill up the textbook. It's like you can achieve security with no quantum key distribution if a single photon, BB84. There's even direct communication protocols recently. You know how you can increase just one entangled pair the communication efficiency, but then encoding and so on. So really, all the beauty is between, I would say, one photon and one entangled pair. There's a very rich framework. People are asking the question, wait, is there something else we can learn? Is there something in between where we still see a quantum advantage if it be not only just a pure single photon or an entangled state? Is something interesting in between? And yes, the answer is there is something. You can work with the superposition of a single photon. That's now, for me, a slightly different concept. Also for communication tasks. And it was shown that from Borivoy, Dakic, and Flavio in Vienna, that you can also enhance the communication efficiency such that one single photon allows the 2 bits communicated. It's super beautiful, and I hope that after my few slides you will see, man, it's so simple, but again, a very, very nice concept where you might think, why haven't I thought of such a beautiful idea with a single photon? Good. Well, we did the experiment, and then something what's nice also in the laboratory, once you dig in, because you want to understand the theory, you want to build your setup, you have to think twice what you want to do, because it's an effort, you know, it's not that easy to build a thing. You learn more about your tasks, and it turned out that you can go even one step further. There's not only improvement in communication efficiency, but also you can achieve nice security tasks, which for our group, security is a main issue. We like to think about security applications for computers and communications, and that was fitting right into our group spirit. So what's the task? The task is you have Alice and Bob who are separated, and each of them want to know the other person's state or input. Okay, so it's defined in the framework that if Alice and Bob, each has an input A to Alice, B to Bob, they get an output X and Y, and each party wants to know from the other one what the output state is, or the output result. Now, how can you do this? Well, you can send even one photon from Alice to Bob, and then Alice prepares again and send it back to Alice to Bob to Alice. So basically you go twice the way, one and twice, that you can communicate the stuff. Or you send 2 particles that cross, okay? So when you, that's basically the classical way how to send these 2 bits. When you now change the game that the distance is chosen such that or the time is chosen, that there's not enough time to go back and forth, okay? So it's shorter than twice the time it takes to go from to both parties. Then you have a problem, because then we'd like to know how can if one particle only achieve that both sides know what can be done. It's very easy to show that in the case where the time is shorter than the distance twice, here and there, the best thing you can do is to have only 1/2 success probability for that both parties know what's the state of the other one. In other words, only one party knows what the other one had as input, but not the other party as well. Okay, as simple as that. However, when you now take a quantum particle that's a superposition of both sides, then you can improve this kind of probability, as shown here. So what you do is now you have an input state which is superposition of Alice and Bob's party. Now both have access to to basically encode the information, the input bit. And what they do is they make a phase flip, basically, as shown here. So X and Y, and they apply phase shift with this modulo of X and Y into the superposition states. In a physical picture, that means you apply a phase shift, and now you introduce this kind of beam splitter here as a mechanism to read out what they have done with the state. And it turns out when you see the results of these different combinations here that say Alice put value 0 and Bob did value 0 and so on, these 4 different combinations, then you see there's a parity symmetry. If both put the value 0 and both put the value 1, then you see the photon ends up at the same state A. Okay, this oval phase we can ignore. However, if the parity is different, 0, 1 or 1, 0, then you see they end up at a different side B. Okay, so now by combining the knowledge what Alice or Bob individually have put this number, plus knowing the overall result where the photon came out, allows you with 100% certainty to tell what the other guy did. Okay, in other words, if I know what I did, I know what the other one must have done to get this output photon at this particular case. So if people are familiar with a Mach-10 interferometer, which is at the cornerstone of optics, it's immediately obvious. What you do is you have a single photon that's superimposed, and it goes to Alice and Bob. They apply now here these are phase shifters, and at the end they obtain a photon coming out either here and there. And again, if they know, for example, I have no photon coming out here, but I did this phase shift here, then I know what the other one must have set in there that I don't see a photon here, or vice versa. If I see a photon and I know my phase shift, so that's a very nice concept to really use one superposition, one photon superposition that both sides can communicate. Okay. Again, it's really one of the similar for me, almost as beautiful as the bomb experiment. You just take a Mach-10 and you see some things as now, well, that's obvious, but really beautiful to see that you can really do something nice for quantum information tasks by this simple concept of a superposition of just one single photon. Now, as an experimentalist, you try to make you do the test, you build such a parameter. You have to, then comes the challenges. You have to design the source. There's only one photon in the setup that you really prove, well, within this propagation time, we don't send a second photon. We really want to convince ourselves this protocol works. We had to, therefore, decrease the power of the laser to have basically not too many photons coming out. The challenge here was, which I think is nice, we had to make this interferometer stable, because what Alice and Bob are doing, they implement a phase shift, okay? And the phase shift means you have to keep the arms stable within the coherence length of the single photon, which is a challenge, as you see here, because you have to build such a big interferometer. And I think it's nice to show that new interesting physics can be done by such bulk optics, huge interferometers, because nowadays the trend is certainly towards integrated optics where you try to minimize and so on. Sometimes you see it's not needed. You want to have something opposite to establish this kind of experiments. So that's basically the setup. Here's the source, the down conversion source, the laser. Can't find here's the down conversion crystal. Here the single photon couplers and so on. That was used then for the experiment. Again, also here, you want to check that you have done the job properly. Again, a nice way to test that this is really the right result. You have a perfect aligned setup, which is interference quality 1, 100% visibility. When you now detune the visibility by changing the arm lengths such that the photons do not interfere properly anymore, then you can see how the success probability goes down as shown in this curve. Okay. And the students have really done a great job. They tried to optimize everything. We also have a very good single photon source. So the G2 second order correlation number tells you more or less how good your single photon is. In other words, how likelihood is it that there's just one single photon, not a 2-photon state or noise contributions. 0 is the best case, so we're really very close to a pure single photon state in there, and that was used for the setup. So to show that this framework works, that you can really communicate 2 bits, okay, in a time that's smaller than it takes to go from one side and to the other side, we put numbers together, and we had to also optimize our detectors to be fast. So the setup was built that it takes 10 nanoseconds to go from Alice and to Bob, okay? So in a nutshell, each distance is 5 nanoseconds. So what we have done on the experiment is we implemented the protocol with all the technological overheads and readout times and jitter times of detectors. which allows to achieve the result in the order of 7 to 8 nanoseconds. So physically, in a shorter time frame than it would have taken to go from A to B and B to A, you could achieve this kind of two-way communication, which also indicates that this protocol works in a nice way. Good. The thing that came out then surprisingly was, well, you can even do something more. So I guess the communication part is obvious. The nice twist on top of that is that you can achieve security and some, we call it anonymity. So it means it's anonymous who is sending to whom the message. So how does it work? It works that you now, again, instead of the same encoding, you have a superposition of one particle where they can, basically each side can now apply a phase shift. So now if you change the rule that you say, for example, one party, Alice, puts a phase shift for 0 and 1, okay? Basically 0, 1, 0, 1, 1 message in one way. Then what Bob is now doing, he puts random pattern of 0 and 1s, okay? So if Alice now puts the message and Bob puts his random noise, then if they read out the overall result of the beam splitter, then of course Bob knows, Bob is the guy who put the random settings, what Alice was transmitting, because he knows his setting and he basically can subtract his contribution there. He knows precisely what the other one was communicating. For the outside person who just looks at the output of the interferometer, he or she cannot tell who was communicating because they just know the overall parity results, but they cannot infer who was contributing with a noise pattern and he was contributing with the message in there. So by that you really hide who is sending Alice or Bob in a nice way. Okay? So that's my words here, more or less in a little bit short mathematical concept. So you have either Alice has the message bits and Bob has the random bits, or vice versa. And only the parties itself know who is communicating. Okay, so that's a nice twist in here. And that's basically allowing on one hand security, because an eavesdropper, once you assume the source is basically a safe third-party contribution, then ignore this problem. An eavesdropper can just look at the output of the Marzehnder and cannot tell who is communicating and not tell you who is communicating what. Okay, that's a nice twist on this experiment here. So the security, and therefore it's also hidden who's putting the message and who's putting the random bits. So these are the results. This is not a cartoon of my son. It's really like something we did in an experiment. So the protocol is that Alice basically puts in a message, but we put 0 and 1s as a pattern for a graphical representation. Bob puts his Bob puts his random things. In a second, what you see here, he retrieves, for example, this pattern, and I tell you why it's not very good. But never mind, all the time, the eavesdropper can just see the overall results of the system. So what I want to show you here, as I said, it's just one photon involved in the experiment. And having no photon received, for example, if you have the setup, and I know that overall I do not have received the photon, but I put a phase shift, then I assume that the other one must have received the photon, and the story works. The problem is, in the major challenge, if you have photon loss, then I get the wrong bit, because the photon might have happened that it came to my port, to my detector, but it did not arrive. So therefore I would give you the wrong result of what the bit was. So if you have the real life conditions where there is in the order of 75% loss, then we see that Alice sends this message, but Bob retrieves more or less this noisy picture, because a significant amount, 25% of photons, are not received, and they add to the noise and give you the wrong picture. However, we had smart students who realized actually you can overcome this in a secure way. How? Send more photons. So what we have done is we tuned the probability to send now photons for the same bit. So when you increase now for, let's say, a 3-photon case, a 5-photon case, then you have some kind of redundancy, which is not jeopardizing your security, because at the end, there's still a random pattern associated, and you just know the overall result, the parity check for the eavesdropper. So by increasing by a nice technical access in your laboratory, the number of photons you send, some kind of redundancy, you can really achieve almost 100%, 90% fidelity of the message you're interested to transmit in a secure manner. Okay, so sometimes error correction can be very simple, in contrast to the nice overview we heard yesterday, where you have this nice framework of stabilizers and so on. Sometimes it's really just send more photons to overcome these limitations. Good, and these are basically the people involved in this experiment that we just did. Oof, okay. So what have we done? We showed that this two-way signaling works with a single photon. We implemented this no security concept, and we are interested now in follow-up experiments along the line. So please stay tuned. You might see something in a couple of weeks on archive. Yes, and I've shown you also error correction for that. Good. Still 20 more minutes to go. If you are not falling asleep yet, I would change the gear again and go to something that really excites us in terms of what quantum physics can do to you for realistic applications. Okay, and it's a spirit of secure computing where we realized that feasible quantum technology allows to implement so-called one-time programs, which as next step allows to perform a secure computation. Okay, so let me show you what I mean by that. So before, for me, the main asset of quantum computing is the security issue in one or the other way. So honestly, I'm not so much excited by the speed up, which is a nice thing to have, but honestly, secure computers, classical computers work very, very fine for many applications if you do not want to simulate quantum systems, but for many things they're just fine. Okay, but security is really something where I see my as a discrete jump for useful applications. And of course, security is an everyday issue when you keep in mind that our data is in clouds, we have Facebook, Gmails, everything there basically is really like it's plain text to servers and so on. So therefore, so many computer scientists investigated what can be done, and it's really an interesting challenge in the field to find secure protocols, and there's a class of different encryptions. One thing that got the interest even in cartoons is so-called one-time programs. One-time program means like here, you know Inspector Gadget? Who is not knowing Inspector Gadget? Oh, okay. Inspector Gadget is this clumsy inspector who gets at the beginning of the scene the message from his boss, please do this and that. Okay, that's the job. But he's a spy. He's like a secret agent. So what does a secret agent has to do? He must be secret. Also, the message must be secret. So in the cartoon here, once you read the message once, it destroys itself. You know, there's also movies like Mission Impossible where he gets the message and then he throws the glasses away and they explode. So that's a standard case of one-time programs. So you see it here. So you can phrase it also in Alice and Bob picture that somebody owns a software. He basically wants to give it to, so Alice has a software, gives it to Bob. Bob can use the software only once, and then basically it's not useful anymore at all. So in a computer language, what you would like to do, you would like to have that Bob can only run a program once, which is coming from Alice. On the other hand, you also want that the person who has the program, Alice, doesn't know what the other person is doing. So if you think about computations, then you provide a function f, which you can only apply once, and you don't know that the person who provides the function, the computer software, can also not learn what x, the input was to this function. That's the framework you would like to have. Okay, you can see the immediate relevance. If you have such one-time programs, then of course viruses are no issues anymore because you cannot learn from the program how it works. The copy protection is there. You cannot copy it because after running it once, it's gone. So you see there's a variety of useful applications for such one-time programs. Even though they're nice, and introduced already a couple of years ago, there's a challenge. There's a fundamental problem. The fundamental problem is it cannot be done for classical computers. The only way, because computers are always there and you can always rerun a program as often as you want. The only way to implement this one-time programs is you really destroy it by physical means, okay, like this kind of bomb there, and then basically you really have it gone, because otherwise software is not, it cannot be erased in there. Well, we are all quantum physicists, and it's a natural question, well, when you're familiar with cryptography protocols and no cloning and the measurement is something that's bad because it changes the state, is there something that can be done by quantum physical tools? And it turned out, unfortunately, it's possible, okay? So there's no way to make a perfect one-time program, and the reason are, again, cornerstones of quantum physics. If you would be able to do it, you would either violate bit commitment, oblivious transfer, all those things which are more or less related to no cloning or these kind of arguments in there, okay? So at some point, there's always a hard reason why it cannot be done, but you can do something still very interesting by having access to quantum technology. So the question was, can we still build a device or build such a one-time program if we relax a bit the assumptions? So you can always choose what to relax. And it turned out you can achieve one-time programs if you be happy that it's not perfect successfully. It means that you have a success rate which is not 100%, but still way better than in a classical case. And basically something I would like to show you now, how you can implement such one-time programs to really protect classical software in computers. For that, we have to understand how a computer works. So a regular software, whatever you have on your devices here, is basically a program. Now, when you look at the logic synthesis, that's the way how computer scientists look at that. Then you can break it down into logic tables. If you further zoom in, they're all existing just of computer gates. You notice standard gates, not AND gates, OR gates, and so on, which always 2 inputs, 1 output in the computation as shown here. So you might have seen those truth tables that 2 input bits define the output bit, and you have basically these drawings here which define the functions. You have 2 or 3 input bits and coming out there. However, all of those gates can be further decomposed into just single qubit gates, where you have now basically something like this, that you can decompose the 2 single qubit gates, allow you to build a 2 qubit gate by classical adaptation of the output results. Okay? So you might ask, how can it be? Here you have 2 inputs and just 1 coming out, and if you have not 2 input circuits with 2 outputs, how can I fuse them to 1? Very easily, there are classical rules and regulations, so this can be done. So long story short, everything can be rephrased by just single qubit gates in terms of classical computers. So the one-time program we had, we were building, and this works in the following. We have now a program that is encoded now in this kind of single qubit gates, and these single qubit gates can be rephrased by quantum truth tables. Okay, basically, there's a unique identity for each gate, and the point is that these single qubit gates are now encoded in quantum states. And we send those quantum states, the single photons, to Bob, who receives them, and now how does he implement his information? He takes these quantum bits, the single photons, and then the measurement setting defines the input, and the measurement outcome defines the output. And obviously, the state of the photon defines the software in between. So stay a bit here, because that's my take-home message. Then I will go into more detail. It's rather late, so if you take just this slide as the take-home message, I'm already happy. So again, you encode the software, each gate in a single photon. You send it to Bob, and Bob chooses 0, 1, and 0, 1 is defined by one or the other basis measurement, and the output to that corresponds to the output of the software, and by that you can then put those things together to get your classical software running. You see the security immediately. Once the photon is measured, the state has been changed or detected, so it's gone, so you cannot reuse the photon again. And obviously, the person who provides a single photon has no idea what you are measuring. Okay, so it's your result over there, and of course, both sides have their security situation in a nice way. Good. As I said, these single qubit gates can be put together. So what we have to do then, if you be more carefully, you take the single qubit bits and you put them together by classical regular AND or OR bits. And as I said before, the input 0 and 1 is defined by, in this case, measuring in one basis or the other basis. And then the results are here combined by very simple classical means. At the end, you can really get the same result as if you would have had a 2-bit classical gate. So what do we have to encode now? And that's again, the beauty of quantum physics can be found in here. So what do we have to encode? In principle, there are 4 existing single qubit gates. If you have access to those 4 different gate combinations, you can do everything for classic computing. What are they? Well, there's just a regular identity gate, so 0 gate that no matter what you put in, 0 comes out, or the 1 gate, no matter what you put in, 1 comes out. There's the identity that it's not affected, so the input is the same as the output. And there's the NOT gate, which just flips 0 and 1. If you have access to those 4, you are in business. So obviously, when you now hide these kind of gates that you were sending to Alice, then you of course cannot extract the underlying gate structure and cannot extract what the software looks like or how it's built up. Okay, but she can use it because she can still provide your input to those systems. So the challenge was, can we hide now these single qubit operations such that the receiver cannot extract the information but still use it? And for that, we used the framework of quantum random access codes. Also a beautiful concept out there for a couple of years. I missed the reference, I think, and it's here, or almost 20 years out there, which raised the questions, if I have a qubit, how many bits can I encode? So nowadays we know qubit can only store 1 bit of information, but you might ask the question, can you still do something better? So the question was, if I have now 2 classical bits, can I encode them in a qubit? And if so, what is the benefit? Can I extract with higher probability the state of my system? So that's basically how people phrase it in quantum information language. You have a bit string of n bits, you encode them in a state, and you basically want to have somebody that's able to basically choose, now I want to measure the second, the third, or the fourth qubit out of my state. Okay, so random access code means I pick out, I can even choose which bit I would like to measure, and ideally I get the right result of the encoded state. So for one, it's very simple. If you have a Bloch sphere, you choose, for example, one basis, and the 1 bit is encoded just by being in a state 0 or 1 in superposition. It's really like a very simple case to follow here. If you now plan to encode 2 bits, then you do something like this. You have this Bloch sphere now. It's enough to stay in the plane. Now you can encode 2 bits as having 1 bit, as shown here, encoded in this basis, and the other bit in this basis. Now when you prepare the states in these kind of 4 possible state vectors, then you can see how it goes. So you have the state here, this is the first bit, either here 0 or 1. The second bit here is either 0 or 0 or 0 or 1. So you can encode here, basically the first bit is in the first position, second bit in the second position. If you'd like now to read out the first qubit, then you measure along this basis. Let's say if the first qubit was prepared now to be in a state 0, then you see there's a high probability to get this kind of result. It turns out it's 85%. So the long story short, the best you can achieve is 85% probability to retrieve the right bit when you basically choose which bit you would like to read out. Okay, that's a quantum random access code. However, still nice. You can do better than classically. You really have this kind of 2 bits encoded in the system. So this framework built the basis for encoding our 4 different single qubit operations. So 1 bit had now 4 different operations involved. And by choosing the right setting, you can retrieve these gate operations with the right input. Let me show you what I mean by that. So what we've done now is we took a single qubit, and we choose 4 different states as shown here, which encoded either constant 0, constant 1, identity, and not. So when you now, that's the encoding. Now the other side was about or input 1 to the gates, where then the output told you the output corresponded to the encoded state in there. So let me just show an example what I mean by that. I know it's already pretty late. For example, when we encoded NOT gate, which is done by preparing this kind of state vector in a Bloch sphere, and you would like to, let's say, we would like to measure in the as 1, so as you measure here, okay. Then you see basically that there's this kind of projection possible on this basis here. If 85% you get, even though input 1, you get as output of your measurement that you measure here, the 0 answer, okay? So by that you really were able to extract the right operations from the single qubit gate, okay? So see from the silence now, that's like advanced time of the concept. So again, it's just like the trick was to encode four different functions in a single photon, and you can really, with high probability, obtain the right computation out of that. So that was it. So as I said, for classical computers, we need these bit gates. So actually one is not sufficient. You have to combine at least 2 single qubit bits to get the standard archetype gate for your computer. That means if this is the success probability for 1, now you have to take 2. It means that the overall success rate goes down to 75% for your gate, which is in principle not bad, because that's still above the threshold of how you can use classical means, classical methods to drive your computation towards 1. Okay, so in other words, you can still be at the end have some kind of majority runs or other mechanisms to make the computation deterministic. but what then jeopardizes the security. So we worked, now I jump a bit to the side. The results of the experiment were rather, I would say, not that easy, but straightforward to retrieve. That was a year. It took another year to do all the calculations with our theory group in Singapore, Joe Fitzsimmons, to investigate the security issue of such a computation. Okay, so we're happy with 75% success rate. Be unconditionally secure of your computation, but you might not be happy from some cases if you have some errors at the end of your computation. And have redundancy implemented in the circuit, then of course you minimize the security that you have, but it's not that straightforward to tell how much this is happening. And if in the most general framework of having POVMs, memories, and so on available, it seems you cannot have that many copies to have 100% success rate. Good. That's the setup. The setup is nice because it can be just single photons are sufficient to implement this kind of one-time programs. Again, there's a down conversion source, one photon, so you get two photons. One is the trigger, other one is prepared here. One of those four different single qubit gates, that's the L is the software, and now it sends the photon bang, 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 bang as the software to Bob, who used the software once for implementing now his or her inputs as needed for the program itself. Okay, these are just technical parameters which tell that we had a pretty good source. We also had here to tune everything with switches, that there was really just one photon only at a time coming, that there's no leakage there from photons, and so on. And at the end, the transmission was just 4%, which is very low. The reason is technical issues. We had many switches to define things properly, which at the end, again, lead to loss. As I mentioned in the very first minutes today, loss is the main issue we have to fight for scaling up quantum photonics. And here you see a very bad example where it was fine for this proof of principle experiment, but of course in the future we would like to boost these numbers, otherwise it's a waste of resources. Good. One important thing, how can you deal with losses? That somebody in the middle says, okay, I steal the software and use it for eavesdropping. Well, if you put on top of this protocol random bit flips, okay, that means Alice chooses, let's say, some of the bits as there are, some of the bits that are sent are just linked to a classical bit flip. You can achieve a protection for eavesdropping, because now the scheme works in the following. Alice sends the photons, and Bob must tell, yes, I retrieved the photon. And then Alice says on top of that, please take it as it is, or make a bit flip. And they work nicely, because in the scheme you can compensate easily for such bit flips to retrieve actually the state I had in mind to send to you. Okay, so this kind of classical bit flip mechanism allows to fight against eavesdroppers who man in the middle attacks, or sort of man in the middle, would take away single photons in that respect. So we applied different protocols to this scheme. The one nice thing was to show that you can implement the Millionaires problem in a nice way. Millionaires problem is something we face every day. It's like a millionaire you meet another millionaire and you wanna check who is richer, okay? But you don't want to tell your amount of money. So the challenge is, I want to know I have more money than you, or you have more money than me, but I will not tell you how much money I have. That's the Millionaires problem, okay? The really very hard everyday life problem we face when we wake up in the morning. So this is called Yau's Millionaires problem. It's done in a way that we take now Alice as one millionaire. She puts her information of wealth in the software, okay? So nobody can read it there. And Bob now basically takes the software and makes his measurements, who tell them the measurements depend on his wealth. And at the end, the output just says, you are bigger or the other one is bigger. Okay, so you split the challenge in software, is one millionaire's information, input to the software, other millionaire's information. At the end, you get the result, who has more money than the other. That was done. We had different cases. So if there is a big difference in the millionaires, then it already differ in the first bit of the number. They made a 75% success rate. If you have to be zoom in and saying, well, they're close, but they just differ in the second bit or the third bit, then you see how the probability slightly goes down because of this probabilistic one-time concept of this program. However, there was something that we realized, that even though the success rate is probabilistic, okay, last 2 minutes, we can find an application where, even though it's probabilistic, you have a deterministic situation at the end, okay? No, it sounds like a contradiction. It's not because what we have done is we realized these one-time programs are ideally suited for signatures, digital signatures, where Alice wants to give a signature to Bob, and he can use it only once. Okay. So for those of you not familiar with a signature, what does a signature mean? Signature means I have a key, I give the key to you, you apply the key to the message, that means that's my signature, and ideally it can be used only once, okay? And after you've done your job with my key and your message, after that you basically you separate again, and I can see if I know my if I know my key, is this the right message that you had in mind, okay? So I see the time running through, so I make it quick. So what people do is you take a message, you have a well-defined method, it's so-called you build a hash. That means you have a standard length of text that's corresponding to an arbitrary length of text over there. For me, that's the real magic. I don't know how this works classically, but that's something like I'm really fascinated about hashing, that you can find a unique, say 300-bit hash that encodes a much longer text over there. Then you apply the encryption, which comes now from the quantum mechanical one-time programs. Basically, you get the encrypted text. You can use it, and at the end, you can verify by decrypting your situation. So I see I'm really passing. Time is running through. So the story is once it's encrypted, you decrypt, and then Alice wants to check is the decrypted text really the original text that was basically encoded within the signatures. In one-time programs, we realized now Alice prepares these one-time programs, sends the programs to Bob, who has this message over there, and the message is the input. So basically, each 0 and 1 is now applied to the one-time programs. You get the output result, and then basically Alice can infer from, since she knows what was there, she can basically go back to and say, okay, if I now verify the story by decrypting, because I know my OTPs, it should be the kind of text over there. And by that you have this one-time use of a signature. I have no time anymore. The long story short, if everything is correctly what we've done, for each bit of the hash, we used, for example, 300 one-time programs. As I said, for each qubit, they have 85% error. So if the error is just 85%, you know everything was done correctly. If the error increases, okay, so let's say out of these 300 runs, you have now a sample 230 or even less correct, then you know that there might be one bit of the hash that was used in a different way. So either the message was taken in a different sense, or somebody tried to steal my one-time program, and therefore you see it. So the long story short, at this late time of my talk, even though you have probabilistic results, you can deterministically figure out if somebody was cheating with my signature, which I think is a very nice result for one-time programs. So in other words, you can have unconditional security for digital signature with this framework. Good, there's no time. We're now building a follow-up experiment to say we go to real-life conditions. We want to send it over distance, so that's Vienna. We send it from one lab to the other, these photons, and we would like to have optimize our performances. We will even switch to an entangled source, which has benefits because you can swap this. You can really have a commodity-based source. Stay tuned. I have no time to mention this. We also had different encryption schemes in the quantum computer framework. For that, there's really no time. With that, I want to say thank you to the people who have been involved in this kind of experiment. We had now a long-lasting collaboration with Joe Fitzsimmons, who is a computer expert and quantum computer expert, in particular for security issues in Singapore. And with that, I finished the tour de force by giving you insights about 3 different experiments where actually I should have probably shown only 2, if in this kind of 1 hour. Thank you very much.
Okay, thank you, Philip. Questions?
Oops.
Yep, you.